I'm standing next to Maytal and we're both looking straight ahead, we're seeing two different rainbows. The only way I could see hers is if I was her height in her spot with my head tilted the exact same way, or she took a picture of hers and showed it to me, then I could see hers. We all see our own, and you can never see it from the side up, right? So the leprechaun's gold is always safe. You can never get the leprechaun's gold because you can never get there. The rainbow turns with you. If that's the case, how could the rainbow be a collective sign for Klal Yisrael when everyone sees their own one? We all don't see the same one. That's like the big question. And the Mefarshim, the Ramban, and Rashi, and others that Mrs. Pogonitz is going to take you through is really going to shed like a lot of, not to be funny, but shed a lot of light on this question and tell you what's going on. So let's understand how rainbows work mechanically before we do this. And so there was a guy named Willibrord Snellius. Yes, that's his real name. I didn't name him. Willibrord Snellius. And we get from him Snell's law of refraction. Refraction is when you bend light. Reflection is when light bounces off and goes somewhere else. And this guy Snell, we know the law in the West from him. It was actually known in the Arabic world about 500 or 600 years before Snell. A guy by the name of Ibn Sal, an Arabic polymath, discovered this. They found in 1992, I think it was, in Syria, papers that showed diagrams where he actually understood what we call today Snell's law, the law of refraction, but we didn't know about it until way after we learned it from Snell. So although he really discovered it first, we didn't know about it till later. That's why we still call it Snell's law. And Snell's law, for those of you who took pre-calc and those in calculus, we have what's called the sine of theta 1 divided by v1. So that's the sine of an angle divided by the velocity of light of that angle. And that is equivalent to the sine of theta 2 divided by the speed of light in that vicinity. And really, there is a refractive index where the index of the lower region is proportional to the bottom region. This is really Snell's law. And this is why light bends. When you have a glass and you put a straw in it and you see it offset, this is why it's offset. We can predict with great accuracy the amount of bending and how different media bend light at different proportions based on this law of Snell. And we're going to prove it today. We're going to do a geometric proof of Snell's law so we can see it work. And before we do that, we need to think about the geometry of it. So here is an interface. And if we say that this interface is a mirror, you get a beam of light that comes in, and then a beam of light that shoots out, right? And it shoots out exactly at the same angle that it bounces off. The Vilna Gaon knew this. He wrote about it in the El Mishulish. This was known by Euclid. He writes about it in the Elements. This was known in the ancient world and in the early modern world. This is a property of light. So it comes in here. It's an incidence beam that shoots in here, and then a reflection beam that bounces off, right? So if you have a mirror, you shine a light. As you move the light down here, it'll move down here also. If we take a normal line here, which is a perpendicular, this will be the point of reflection. Instead of a mirror, we change this to water, like in your cup. The normal line will continue down, and you might think under normal circumstances, hey, this beam will continue to shoot out like this, but it doesn't. It bends like this. And so we get a right triangle in here, and we have a right triangle in here. And so this angle here we'll call theta 1, and this angle in here we're going to call theta 2. And so the proportions here, theta 1 proportional to the speed of this beam is equal to theta 2 proportional to its beam, which means that the speed of light down here divided by the speed of light up here, or the refractive index. So when you go to the doctor and they fit you for glasses, they look at what's called diopters, and they use this refractive index to figure out how your glasses should be, because your eyeball actually, when light goes into your eye, there's liquid in there, it gets refracted based on this, and your eyeglasses have to account for that, otherwise you'll see things all whacked out. This is actually very practical, comes in a lot of areas.